In this video, we are continuing our look at chiral molecules, focusing on physical properties of chiral compounds. If we compare a pair of enantiomers, such as R2-butanol and S2-butanol, if we were to compare the melting point, boiling point, density, these depend on intermolecular forces. The intermolecular forces holding a sample of this molecule together will be the same as the intermolecular forces holding a sample of these molecules together. So the melting point, boiling point, density, these are going to be exactly the same. If we think about thin layer chromatography, gas chromatography, or high pressure liquid chromatography, these are all based on interactions with achiral stationary phase, mobile phase, and the emphasis is on differences in polarity in general. While the polarity of these two compounds is the same, so their behavior in TLC, GC, HPLC will be the same. What about spectroscopic techniques such as IR and NMR spectroscopy? Well, IR we've already talked about, looking at bonds and functional groups. Those bonds are the same in both molecules. NMR is based on the proton environment. That's going to be identical. And so the spectra are going to be the same for both compounds. So all of the physical and spectroscopic properties are the same for a pair of enantiomers, with one exception. So one property that differs between enantiomers is called optical activity. And this is the ability to rotate plane polarized light. Enantiomers will differ in the direction of rotation. So all physical and spectroscopic properties of enantiomers are the same except for optical activity. Enantiomers will rotate plane polarized light in opposite directions. All right, so what does this mean? Here we have a schematic of a polarimeter. So we have a light source, and in general, light waves will be moving up and down in this direction, but they'll also be moving in this direction and in this direction. So the light is unpolarized. But if we put in a polarizing filter, then this light, this light, this light will all be blocked. Only this light will be able to pass through. So now we have plane polarized light. It doesn't go side to side, only up and down. Once we have this plane polarized light, this can pass through a sample that has a solution of a chiral compound. And that chiral compound will rotate the plane polarized light, either in this direction or in the other direction. So what comes out after the sample is now rotated relative to what we started with. Then we have an analyzer, which itself could be another polarizing filter. And if this is straight up and down, now that this is polarized, it'll be blocked and the observer will see no light. But if you rotate the analyzer to match the new angle of the rotated polarized light, then you will be able to observe light passing through the analyzer. So with our light source, and then we have our polarizing filter. And so the light coming through is going to be moving in a single plane. And then if we have an analyzer that's lined up the same way, then the detector, or it could be just the observer, they will be able to observe the light because it will pass through. If we have the same setup, and here's our light source, here's our filter, and the plane polarized light is moving in this direction. But now we have a sample of something that is optically active, then it will rotate the plane polarized light, and it could rotate it to the right or to the left. Now, if the detector still looks like this, then the observer will see nothing. But if the analyzer is rotated to where this angle matches this angle, then the observer will be able to see the light. So then by looking at whether this analyzer is turned toward the right or toward the left and how many degrees it's turned, this gives us information on the optical activity. As we think about the rotation of plane polarized light, a compound that rotates the light clockwise to the right is called dextrorotatory, and a compound that rotates the plane polarized light counterclockwise or to the left is called levorotatory. Early on in this chapter, I mentioned that medications have to be made with only one enantiomer rather than as a mixture of enantiomers, or else they have to be able to show that if one enantiomer works, the other one does no harm. Well, many medications are made only one hand, and for example, you may have taken some dextromethorphan, which is a cough medicine. And so this is the enantiomer of methorphan that rotates plane polarized light to the right. If you have an underactive thyroid, you might need to take levothyroxine. This is another medication, and it is the version that rotates plane polarized light counterclockwise. Now, dextrorotatory is given the symbol plus, and levorotatory is given the symbol minus. Now, this has nothing to do with charge. It only has to do with the direction of rotation of plane polarized light. If we consider a chiral molecule, it has a particular electronic environment, which is going to have a particular interaction with light, leading to a rotation. Now, the enantiomer, this is the mirror image, it is going to have the opposite electronic environment. So it has the opposite interaction with light, and so it rotates in the opposite direction. Now, is there a relationship between RS and between plus minus? Knowing that something is R does not tell us whether it is plus or minus. Knowing that something is S does not tell us whether it is plus or minus. If we find out that the compound that we would give the R configuration, if that happens to be, if R is plus, then the S will be minus. But for other compounds, you might have R is minus, then S would be plus. So just knowing R or S won't tell you if it's going to be dextrorotatory or levorotatory. But once you figure out one of them, then you know what the other one would be. So keep in mind what we're talking about. This is the configuration R or S. So this gives us information on the physical arrangement of the atoms. And then this tells us about the physical property of optical activity. So if we have a sample of an optically active compound, how much is the plane polarized light going to be rotated? Well, let's say two students measure the optical activity of samples of S2-butanol. So the first student made up a concentration of 250 grams in 100 mils of solvent. They used a polarimeter cell with a length of 1 decimeter. And what they measured was an optical activity, this is the rotation, of plus 33.8. So we have the concentration, we have the path length, and then this is what's observed on the polarimeter. Student 2 also made up a sample of S2-butanol. Theirs was 200 grams per 100 mils. They used a polarimeter cell with a length of 0.5 decimeters, and they measured a rotation of plus 13.5. So this seems like a problem, but we have different samples. So rather than focusing on the rotation of a particular sample, instead we consider the specific rotation. So that has alpha in brackets, and this is defined as 100 times alpha, the measured rotation, divided by C, the concentration in grams per 100 mils, times L, the path length, in decimeters. So alpha is the measured rotation, C is the concentration in grams per 100 mils, and then L is the path length in decimeters. So for student A, we have 100 times 33.8 divided by 250 divided by 1. And if you plug that in, what you would find is a specific rotation of 13.5 degrees. Now, student 2, if we plug in the values, the specific rotation is 100 times 13.5 divided by 200 divided by 0.5. And if you plug that in to calculate, this gives you a value of 13.5 degrees. So we have the same value. So the measured rotation is only of limited use. Mainly, we're going to focus on specific rotation because that gives us something that we can compare. All right, now let's go about this a little bit differently. Let's say we have 3 students who tried to prepare a sample of S2-butanol, and the literature value for the specific rotation is plus 13.5. So let's say student 1 made up a sample of 500 grams per 100 mil, used a path length of 0.1, and measured a rotation of 6.75 degrees. So the specific rotation then would be 100 times the measured rotation, which is 6.75, divided by the concentration, which is 500, and divided by the path length, which is 0.1. So this gives a specific rotation of plus 13.5 degrees. In the second example, a student made up the same concentration, same path length, but they measured negative 6.75. So here we've got 100 times negative 6.75 divided by 500 divided by 0.1. So this gives a specific rotation of negative 13.5 degrees. And then the third student made up a sample of the same concentration, same path length, but they measured a rotation of 0. So their sample did not rotate plane polarized light. So 100 times 0 divided by, who cares about the rest of it, this gives a specific rotation of 0 degrees. So what's going on here? Let's say that the students did confirm by IR, by other methods, that they did obtain 2-butanol. But now the optical activity is going to determine whether they made S2-butanol. Well, student 1 obtained an optical activity that matches the literature value for the specific rotation of S2-butanol, and so this student made the desired compound. Student 2, they have a sample that has a specific rotation of negative 13.5, not positive 13.5. Well, this student made R2-butanol. They made the enantiomer. Knowing the literature value of S is plus 13.5, then we know that R would be negative 13.5. Now, what's going on with student 3? If IR and other evidence confirms that they made 2-butanol, but there is no optical activity, what must have happened is that this student made a mixture of R2-butanol and S2-butanol. When you have an equal mixture of a pair of enantiomers, this is called a racemic mixture. So a mixture that has an equal amount of a pair of enantiomers is a racemic mixture, and it will have an optical activity of 0. So let's think about, here's our light source, and we have our polarizing filter, so our light comes through this way. Now imagine if we had a sample of R, that would rotate light in one direction, and then if we had a sample of S, it would rotate it in the other direction, which would bring it right back to the original angle. And so what we're looking at then would be a rotation of 0 degrees. So in this case, we're not talking about having separate samples. We have an equal mixture of R and S. If the plane polarized light bumps into a certain number of molecules of R, which would rotate it to the left, and then it also bumps into the same number of molecules of S, it's going to rotate it to the right, and the net result is no rotation. So here we have examples where it is pure S, pure R, and then a 50-50 mixture of S and R. It's also possible that we have a mixture of enantiomers that is not a racemic mixture. So maybe it's not 50-50, maybe you have an excess of the dextrorotatory. Then you can calculate what's called the EE, the enantiomeric excess. And this gives you information on how much of the plus and how much of the minus you have in solution. We're not going to do those calculations, but I just want you to know that it is possible to have all of one enantiomer, all of the other enantiomer, a 50-50 mixture of enantiomers, and everything in between. So let's come back to this idea about a relationship between RS and between plus minus. So on paper, we can draw a sample of R2-butanol and S2-butanol, where the R and the S are determined by the Conning-Prelog rules. And so the R and the S, this refers to the absolute configuration. Now in lab, you can have a couple of samples, and let's say by boiling point IR NMR, you know that it is 2-butanol. Using a polarimeter, you can find that one sample rotates in the plus direction and the other sample rotates in the minus direction. But to determine whether the plus or the minus goes along with the R or S is actually not straightforward. If it's the very first time a compound has been synthesized, figuring out whether it rotates plus or minus, well, that can be done with the polarimeter. But figuring out the one that's plus, whether that's R or S, that actually takes a lot of effort. So I want you to keep in mind that once we know the direction of optical activity of one enantiomer, we know that the other enantiomer will rotate in the opposite direction, right? Same magnitude, but opposite direction. But I also want you to appreciate that figuring out which is not necessarily easy to do.